This video is going to cover magnetic fields part 2 for Special Higher Physics 1B. We're going to start by looking at the Hall effect. One place where the Hall effect is applied is in the magnetic field sensor that you're going to be using in the laboratory exercise, magnetic fields and the slinky coil. So let's consider what happens if we have a piece of metal like this, placed in the magnetic field. What we'll do is we'll run a current along, let's call it the x-axis of the metal, and we'll apply a magnetic field this way in the y direction. And let's consider a positive charge here and work out what force is that positive charge going to feel. Well, we know that F is equal to QV cross B. And as it's flowing in a current, it'll have some drift velocity in the direction of the current. So you can see it's going to feel a magnetic force. In this case, using the right hand rule, that magnetic force will be up. So as it feels a magnetic force, it will respond to that magnetic force and it'll move up to the top. We'll get a collection of positive charges up the top here, which will mean that there's associated negative charges down the bottom. So you can see this is going to generate an electric field. So the electric field will be going like this inside the metal here. So that's going to cause this positive charge to feel an electric force downwards. So this will be Fe. And these charges will keep responding to these forces until the forces reach equilibrium, so until there is no overall force on the particle. So we have that Fb is equal to Fe. And the magnetic force is given by QVdB, and the electric force is given by QE, and we'll give it a little subscript h for the Hall electric field. So these Q's will cancel out, and this will give us our Hall electric field. Now, what we actually measure in things such as this magnetic field sensor is the voltage difference between the top and the bottom of the metal slab. So let's call this a distance d. So we know that the potential difference between 2 points is the electric field times the distance. So we have that the voltage difference, we'll call it the Hall voltage, is EHD, which is equal to VDB times the distance. So where this is the drift velocity, which comes about due to the current. So we can easily measure D, that's the height of our piece of metal, B, the magnetic field, that's generally what we're trying to measure, VH, we measure the potential between the top and the bottom. So how can we write VD? Well, let's just remember what we did about charge density before. We said that the charge is equal to the charge density in the normal direction times the surface area times the time. And we know that current is just charge over time. So this tells us that the current is equal to J dot N delta S, where this is the area. We also saw that we can write J as the charge density times the drift velocity, and that's, instead of writing delta S, we'll write the more normal A, the surface area. So in this case, this would be the surface area here, the surface area through which the current is passing. And finally, we can write this charge density as the size of each charge times the number of charge carriers per unit volume, VDA. So that's equal to I, and let's substitute that in for VD here. So we have that our Hall voltage is equal to I over QNA times BD. So if we want to call this distance here the thickness, we could write that our area, the area is TD, and this is BD, and so these D's cancel out, and we've got IB over Q and T, where T stands for the thickness. And N is the number of charge carriers per unit volume. So N is not too hard to calculate for some metals such as lithium, sodium, copper and silver, which all give up one electron to the sea of electrons which conducts the current. So just by knowing the atomic mass and the density of those substances, we can get the number of charge carriers per unit volume. For more complicated atoms, it is harder to work out how many electrons each atom is going to give up, and we'd need to use quantum mechanics. Let's do an example of this. Imagine that you have a rectangular copper strip 1.5 centimeters wide and 0.10 centimeters thick. So let's just draw it here. This is 0.10 centimeters. This is 1.5 centimeters. Here's our magnetic field B. Here's our current I. And we're told that I is equal to 5.0 amps and B is equal to 1.2 teslas. The magnetic field is applied in the direction perpendicular to the strip. We're told that the density of copper is equal to 8,920 kilograms per meter cubed, and that the molar mass of copper, or the atomic mass, is 0.0635 kilograms per mole. And we're asked to find the Hall voltage. So we'll need to use the equation that we derived. We'll need to use that the Hall voltage is equal to IB over NQT. Now we've got the current, we've got the magnetic field, we've got the thickness. We know that the charge carriers are electrons, so their charge is 1.602 times 10 to the minus 19. So what we need to work out is the number of charge carriers per unit volume. So to do that, we can use the density and the molar mass. The density over the molar mass will give us the number of moles per meter cubed. And what we need is the number of atoms per meter cubed. So if we times that by Avogadro's number, we'll actually end up with the number of atoms per meter cubed. So we've got 8,920 over 0.0635 times 6.022 times 10 to the 23, which gives us 8.459 times 10 to the 28 atoms per meter cubed, which is also the number of electrons or charge carriers per meter cubed. So now we can just substitute everything in here. So we've got that our Hall voltage is equal to I, which is 5.0, times 1.2 over 8.459 times 10 to the 28 times 1.602 times 10 to the minus 19 times the thickness, which is 0.10 times 10 to the minus 2. And then solving that on the calculator, we end up with 4.4 times 10 to the minus 7 volts, which we could write if we wanted 0.44 microvolts. So a very small potential difference and a very large magnetic field. So these voltage differences are very small, but it is possible to measure them. What we're going to look at now is the force between two current carrying wires. We're going to imagine that we have wire 1, which is carrying a current I1 and we have wire 2 carrying a current I2. We'll say that they're a distance d apart. We know that a current carrying wire feels a force in the magnetic field given by F is equal to I L cross B. So what we can do is, if at wire 2 we work out the magnetic field due to wire 1, we can then use that to get the force on wire 2 due to wire 1. So at wire 2, let's consider what the magnetic field will be due to wire 1. Wire 1 will have a magnetic field going into the page at wire 2. And the magnetic field strength there will be given by mu naught I over 2 pi d. This is from the expression that we derived from the Biot-Savart law for an infinitely long wire. We'll be seeing an easier way to derive it in a little while, but that's where it comes from. So now what we can do is we can substitute in our values here. So this is talking about the current through wire 2, so that's I2. We'll consider a length L of these wires, so L. So we've got L. Now the size of the magnetic field is mu naught, and this is I1 over 2 pi d, and the angle between the flow of current and the magnetic field is 90 degrees. So for the cross product we'll have sine 90, which is 1, and let's just consider the direction as this is the direction of the current, so to the right, and the magnetic field is going into the page. This force is going to be upwards towards wire 1. So we can write this as mu naught over 2 pi L I1 I2 over D. And this force, if the currents are flowing in the same direction, they'll be towards each other, as in this case. If the currents are flowing in the opposite direction, then the magnetic field here will have the same direction, but the current will be opposite, and so the force will be in the opposite direction. So towards each other when current is in the same direction, and away from each other when the current is in the opposite direction. So that is how you calculate the force between two parallel current carrying wires. What we're going to look at now is an easier way to calculate this. Okay, what we're going to be looking at is something called Ampere's law. Ampere's law is a little like Gauss's law, except that it's for magnetic fields. So we've got B dot ds. So B is the magnetic field, ds, in this case we're considering a loop, so this is a path. Rather than being an area, which is what it was in Gauss's law, is now a path, and this is equal to mu naught I enclosed, where this is the current enclosed by the path. Now this is equivalent to Maxwell's third law in the electrostatics case. Grad cross B is equal to mu naught J. We're not going to show how those are equivalent now because that involves a lot of vector calculus, but this is equivalent. Now, as with Gauss's law, this is only useful in specific situations. Those are generally situations where we have a lot of symmetry. The Biot-Savart law will always work, but Ampere's law is much easier to use if you can. Let's first of all consider a situation where it's not especially useful. Imagine that you have a current carrying wire carrying the current into the page, and here's another current carrying wire with the same current coming out of the page. Let's draw a path around here, And can we get the magnetic field around this path using Ampere's law? Well, the simple answer is no, we can't, because we cannot make the assumption that the magnetic field is constant around this path. Clearly, the magnetic field around this wire, we know, is going to be looking like this, and the magnetic field around this wire will be going in the opposite direction, so it wouldn't be reasonable to assume that a little increment dB here is the same as a little increment dB here. Those are not equal, there's not enough symmetry. And if we were to work out what B ds was, it would in this case be 0. But that doesn't mean that the magnetic field is 0 everywhere. It just means that as you go around the path, the magnetic field lines going into the page will cancel out with the magnetic field lines coming out of the page. So Ampere's law is often not useful. Let's look at a few situations though where it is useful. Let's first of all consider a long current carrying wire. We'll let it have a radius r, and it's got constant current density. With current I flowing through it. Let's assume that the current is flowing up out of the screen at us. And what we need to do is work out B for radiuses less than the radius of the wire, and work out B for radiuses greater than or equal to the radius of the wire. Okay, so first of all, considering a radius inside the wire, here's our little r. We know from Ampere's law that B dot ds is equal to mu naught I enclosed. So what we need to do is work out how much current is enclosed. We know that the current density is constant over this wire here, and across the entire area the current flowing through is I. Only part of that current I though will be passing through this loop here. So we have I enclosed is equal to the area of enclosed by the loop over the area of the wire, the cross-sectional area of the wire, times I. So that is equal to pi r squared, little r squared, over pi big R squared times I. So it's equal to little r squared over big R squared times I. Okay, now we know that magnetic field lines go in circles around a wire, so it's reasonable to assume that B is going to be constant at a fixed radius from this wire. So we can pull B out the front of this integral. We've then got the path integral around this path. Now to work out B dot ds, strictly speaking, we do need to know the direction of the path, but let's just take the direction of the path as the same direction as the magnetic field, which is what you do wherever possible. So there's our direction of the path. And this is equal to mu naught little r squared over big R squared I. So this just means the path length. So in this case it's the circumference of the circle. So we've got B times 2 pi r is equal to mu naught r squared on r squared I. The little r's will cancel out and we end up with B is equal to mu naught over 2 pi r over capital R squared I. And that tells us the magnetic field inside the wire. Let's now calculate the magnetic field for R is bigger than the radius of the wire. So that's this green one. We can take a path like this. So in this case, we've got B dot ds is equal to mu naught I enclosed. And the amount of current enclosed is just the I. So and once again we can assume that the magnetic field is going to be constant here, so we can pull it out the front of the integral. So we've got B times the integral around the path is equal to mu naught I. And the integral around the path is just the circumference, so 2 pi r. And so we have B is equal to mu naught I over 2 pi r. And that is in very few lines of working compared with the Biot-Savart law, where we had to do a lot of working to get to that expression. So when we can use Ampere's law, it's very powerful and saves us a lot of time. Let's now consider another situation where we can use Ampere's law. We can use Ampere's law to work out the magnetic field inside a toroid. So a toroid is a big loop. We'll say it has radius b, and it's made of some circle. It's donut shaped. So we'll call the radius of the material making up the toroid A. And what we want to do is work out the magnetic field inside the toroid, so around some loop like this. So let's draw a loop with radius r inside the toroid. We'll choose a direction like that. And to make this a toroid, we have a wire flowing current around the outside. So the current's flowing like this. We've got n loops of wire. And what we want to know is what is B inside the toroid. Okay, so we've got B dot ds, that's the magnetic field around this path, is equal to mu naught I enclosed. Okay, now the magnetic field, let's just consider how each of these loops of wire is going to contribute to the magnetic field. You can see each of these loops is going to have some magnetic field going through its middle in this direction. So B and ds are in opposite directions, they're anti-parallel. So in this case we would end up with a negative sign. So we've got this magnetic field is constant around this path, so we can pull it out the front of our integral. So we've got B times the circumference of the path, the integral of ds, which is 2 pi r, is equal to mu naught. Now, the current enclosed, we've got n of these loops, each carrying a current I. So this is equal to n I. So we've got B is equal to mu naught n I over 2 pi r. Now really this is a negative as they're going in opposite directions, but that negative doesn't really mean anything. What we should do is state the direction of this magnetic field. So this is going clockwise when we're looking at it from on top. So going clockwise when observed from on top. So this is the magnetic field in here, and you can see it does have some r dependence. So it's not actually constant with radius, it is dropping off as we get further from the center of the toroid. Now, one interesting thing to think about is what's going to be the magnetic field in the center here. Because if we look at this, we've got B dot ds is equal to mu naught I enclosed here. There is no enclosed current, and so we have no magnetic field following this path here. But that's all we can say. It doesn't mean that there is absolutely no magnetic field in the center here. It just means that there's no magnetic field flowing in the plane of the toroid. There is a very weak magnetic field in the middle here, but it's flowing perpendicular to the loop, not around the loop like this, which is why B dot ds is 0. One final case that we can use Ampere's law for is a solenoid. So a solenoid is a coil of wire, something like this. And we can draw an Amperian loop through the middle of the coil like this to work out the magnetic field in the middle of the solenoid. Now I'm going to leave this as an exercise to you You can do this by making the assumption that the magnetic field is equal to 0 out along this part of your Amperian path. Along here we've got B dot ds is equal to 0 as the magnetic field and the loop are perpendicular to each other, so the magnetic field lines are going in this direction, not up and down the page. And so the only contribution to the integral B dot ds comes from this part of the path along here. So use this to work out the magnetic field in the center of a solenoid. What we're going to look at now is Gauss's law in magnetism. Now, with electric fields, we said that the electric flux was equal to E dot dA, the integral over the surface. With magnetic fields, it's exactly the same. The magnetic flux is equal to B dot dA. Now, we were considering closed surfaces for electric fluxes, and we said that around a closed surface, if we have some charge here, then the magnetic flux was equal to the enclosed charge over epsilon naught. And to have any flux through this closed surface, to have a total flux through the enclosed surface, we had to have some enclosed charge so that we could have electric field lines cutting through that surface. Let's consider what happens with magnets, because magnets are a bit different. They're always found as a north and a south pole together. So we draw the magnetic field lines coming out of the north pole and into the south pole. But really we should draw them as continuous lines. So they continue through the magnet like this. So that's clear that that's what happens in a solenoid. You should have just shown that. But it also happens in a bar magnet. So now let's consider trying to draw a closed path. Now let's consider drawing a closed surface around our magnet, and let's see if we can work out how to draw one such that we have more lines entering or leaving it and not an equal number. If we draw a surface such as this, so imagine that this is a three-dimensional surface, then we've got two lines leaving and two lines entering. If we draw it up here, again we've got one line entering and one line leaving. If we draw a surface here, we've got two lines entering and two lines leaving. However we draw the surface, because magnetic field lines always form loops, we'll actually always have the same number of magnetic field lines entering and leaving each surface. So what that tells us is that this integral around any closed surface of B dot dA has to be 0. And this is actually Maxwell's fourth equation. And the result of this equation is that it's not possible to have a magnetic monopole. There's no way we can have just a north pole, like we can just have a positive charge here. Okay, so let's have a look at Faraday's law of induction now. Now, Faraday's law of induction tells us that the EMF stands for electromotive force. It's not actually a force, it's a voltage. So it tells us that the EMF generated is equal to minus N, where this is the number of loops, times d phi b dt, where phi b again is the magnetic flux like we've just looked at. So phi b is equal to the integral of b dot dA. So if we want to change the magnetic flux, there's a couple of ways we could do it. We could have a changing magnetic field, so a time-dependent magnetic field, or we could change the area through which the flux is being considered, so change the area of our loop. Now, one really important thing about Faraday's law is this negative sign here. This negative sign has its own name. It's called Lenz's law. And what it tells us is that the generated EMF opposes the change that generates it. So when we have an EMF generated around a loop, that's going to induce a current to flow. And this current is going to oppose whatever change generates it. So if we have an increasing current producing this EMF, then the induced current is going to try and decrease that current. And if we have the EMF produced by a current which is decreasing with time, then we'll have the induced current is going to try and increase the current with time. So this Lenz's law comes about because of a result of conservation of energy. Okay, so example 1. So in this example, we're told a loop of wire encloses an area A. Okay, so let's draw our loop. Here we go, that's an area A in there. And then it says it's placed in a region where the magnetic field is perpendicular to the plane of the loop. The magnetic field B varies in time according to the expression B is equal to B max times e to the minus AT, where A is a constant. So it's perpendicular to the plane of the loop. So let's draw it going into the screen in this case. Okay, so we've roughly sketched that now. And then it says at t equals 0, the field is B max, which we can see from here. If we substitute in t equals 0, we've just got B is equal to B max. And it says find the induced EMF in the loop as a function of time. Okay, so Faraday's law tells us that the induced EMF is equal to minus n d phi b dt. Now in this case, n is equal to 1. We've only got one loop, and phi b is equal to the integral of b dot dA. Now in this case, the area isn't changing, so it just ends up being b times a. And so this is equal to BA, which in our case is equal to B max e to the minus AT times A. So now to work out the EMF, we've got minus D A B max e to the minus AT dt. And differentiating this with respect to time, we've got minus A B max. Those two constants can come out the front, then we integrate the e to the minus AT. When we do that, we get minus A times e to the minus AT. And so this is equal to A B max little a e to the minus AT. And we can see B max times e to the minus AT, that's just B. So we could write this as A, B, A if we wanted to. Okay, and now as t goes to infinity, we're going to have that B goes to 0 because e to the minus infinity is going to go to 0. And so the induced EMF is also going to go to 0 as time goes on. Okay, so example 2. In this case, we've got two conducting bars, so they look something like this, and they're joined together with a resistor here. So that's resistor. The distance between the bars is L, and then we've got another bar across the top, which also has length L, and it's got mass M, and it's traveling in this direction. We can call it the positive direction with some initial velocity VI. We've also got a magnetic field going into the page here, so into the screen like this. And in part A, we're asked, using Newton's laws, find the velocity of the bar as a function of time. So these are
frictionless. The bar sliding along here is frictionless. Okay, so in this case, using Newton's laws, we'll need to use Newton's second law, F is equal to ma. Now, in this case, as the area enclosed by this loop is increasing, we are going to have an induced EMF. So the induced EMF is going to be equal to minus, now n, that's the number of loops. We've only got one loop in this case, so it'll be d phi b dt, and in this case we've got minus d. Now the magnetic field is constant, it's a constant b, so this is b, and the area is the area of this loop. So let's call this length here x. X is obviously going to change as the bar moves to the right, so the area is equal to Lx, so that's Lx dt. Now, the magnetic field and the length of the rod are not changing with time. So when we differentiate this, we get minus BL dx dt. And dx dt, that's how quickly the rod is moving this way. So this is just equal to minus BLV. So we've now worked out the EMF, which is induced as the rod moves to the right. And so once we know the EMF, we can work out the current because we can use Ohm's law. This is equal to IR, and we're assuming that there's no resistance around here. The only resistance is in the resistor here. So this tells us that the current I is equal to minus BLV on R. Now, current doesn't really have a sign. This will be related to which direction the current flows, but we can say the current is equal to the magnitude of this, so it's just BLV on R. And if we want to work out, well, what direction is the current going, the current's going to try and reduce the magnetic flux inside the loop because the area of the loop is increasing. So in order to reduce the flux inside the loop, we need to have the magnetic field lines by the induced current coming out of the page. So if we want, this is the B induced, and so if the induced field is coming out of the page, we can see that if we're looking at from on top, this is flowing in an anti-clockwise direction. Okay, so we've said from Newton's second law, F is equal to ma. Now the force in this case is the force which comes about from the magnetic field interacting with this induced current here. So this is given by Li cross B. I and B are perpendicular to each other, so this is Lib. Now what we've done is we've worked out how big I is here, so we can substitute this back in here. But just before we do that, we should note the force opposes the motion, so it's in this direction. So the force is in the opposite direction to the velocity. Okay, so we've got m, which ma, and a is dv dt, is equal to lb times I, and I is equal to blv on r. And we've said that the force is in the opposite direction to the velocity. So we're going to need a minus sign there to show that this is negative. So we can now write this as we've got here the length, that should be a lowercase l for the length, lowercase l. So we've got b squared l squared v on r is equal to m dv dt. And we'll move everything to do with a v over to the left, so that's on v is equal to b squared l squared over m r, and that's dt. And now we can integrate. We'll go, it starts from velocity initial, so that's vi, which we've written there, and here we've got vf, and we'll go from time t equals 0 to time t, and so we've got log of v from v initial to v final is equal to b squared l squared t over mr, and this is from 0 to t. So this is log vf minus log vi, which we can write as log of vf on vi, which is equal to b squared l squared t over mr. and we're trying to get an expression for VF. So in order to do that, we can do VF on VI is equal to E. Sorry, I dropped my minus sign. I had it here. We need the minus signs. So that's E to the minus B squared L squared T over MR. And so VF is equal to VI times E to the minus B squared L squared T over MR. So we've now derived an expression for the final velocity, which is what we were asked for. In part B, it then says, show that the same result is found using an energy approach. Okay, so to consider energy, we're going to be losing energy through this resistor here. We know that P is equal to VI. Power is equal to voltage times current. So this tells us the rate at which the resistor is losing energy. So it'll be losing that energy through heat mainly. And so we know that the energy lost by resistor, well, it's energy gained by the resistor and then subsequently lost, is going to be the same as the kinetic energy lost by the rod. Okay, so let's do this with powers. So we know that the power which the resistor gets from the loss of kinetic energy is equal to VI, but we can also write that as I squared R, and we've worked out what I is here, and that comes from the change in the kinetic energy. So change in kinetic energy is given by mv squared. Okay, so I squared, we've got I there, so that's B squared L squared V squared over R squared times R is equal to negative times the derivative of this. Now half m doesn't change, and then we've got dv squared dt, and so this is equal to minus a half m. Taking the derivative of v squared, we get 2v times dv dt. So we can now equate these two things. So one of those r's will cancel there. So we've got b squared L squared over R, and we've got 1v here and a v squared here. So we've got 1v left, and then the half will cancel out that 2, and if we divide by m, that is equal to minus dv dt. Now you can see this equation is exactly the same as this equation that we had up here. So we need to solve this in exactly the same way, and it's going to give us exactly the same expression for the final velocity. The final velocity will be equal to the initial velocity times e to the minus b squared L squared t over mr. So we've shown that if we do this question with energy considerations, it gives us the same result as if we do it with the force considerations, which is a good thing. Okay, we're now going to look at induced EMF and electric fields. So before we do that, let's consider moving this loop of wire over this magnet here. Now the magnet stationary, north pole up here, so there's magnetic field lines going up here. So if we were to move this loop over the top of that magnet, we're going to have an induced current in this loop, which will be caused by we're moving the charges inside the wire, the electrons around the atoms, through a magnetic field. So those charges inside the wire are going to feel a force because F is equal to Q V cross B, and we're moving them, so they've got velocity this way and there's a magnetic field up that way. So they're going to feel a force, they'll move, that's going to induce a current in the wire, and if we're looking from on top, we're going to have I flowing flowing clockwise, sorry, if we're looking from on top. Okay, so in that case, we had a magnetic force causing these charged particles to move. So let's consider the very similar case now, where we now have a stationary loop and we're moving the magnet towards the loop. Now, if we were to consider different reference frames, I mean, this is the same situation, but from different reference frames. In this case, we're in the reference frame of the loop, so the loop stationary, and here we're in the reference frame of the magnet, so the magnet stationary. So relativity tells us that these two should be exactly the same, and so we should end up again with the current flowing clockwise when looked at from on top. But in this case, if we're to consider the force which is acting on the particles in here, well, F is equal to QV cross B, but there is no V because this loop isn't moving, so the particles inside the loop are not moving. And so in this case, it's not the magnetic force that is causing these particles to move. So that tells us that there must be an electric force. So what we're going to look at now is a way to describe this electric force. Okay, so let's consider another loop here. And what we're going to do now is move a north pole towards this loop here. Now, as we move the north pole towards the loop, we're going to generate a, north pole in this loop here coming out of the loop to try and oppose this motion. And so in that case, we'll have the current flowing this way around the loop. And so we can picture the electrons moving around the loop this way. Okay, now what we're going to do is consider the energy around the loop here. We know that power, that's the rate of energy, is equal to VI. The V in this case is equal to the EMF, and I, that's the number of charges over time. That's just what current is. And so we can say that the energy to move the electron around the loop is equal to the EMF times Q. And we also know that the work done on the electron, which is negative, to get it go around the loop, is given by the E dot ds, the electric field, times the distance, and in this case it's a closed loop. So we can write this, and so we know from Faraday's law that the induced EMF, in this case we've only got one loop, so we've got minus d phi b dt is equal to the integral of E dot ds. So that's the general case. Okay, now let's consider this particular case where we've got this circular loop with radius r here. So in this case, we've got d phi b dt. Now we've got the magnetic field. This is the induced magnetic field times the area, which is pi r squared in this case, dt. The radius isn't changing with time. As we move the magnet closer, the magnetic field strength will change. So B does depend on time. And here, if we're moving the magnet through the center of the loop, then I'd imagine that we can pull E out the front because it's going to be perfectly symmetrical. So we'd expect this E to be the same everywhere around the loop, which is why we can pull it out the front. And then the integral around the loop, that's just the circumference of the loop. So that's E times 2 pi r. So differentiating this side, we've got minus pi r squared dB dt is equal to, this is the electric field, times 2 pi r. We can cancel that r, we can cancel that pi. And so this tells us that the electric field generated around this loop is given by minus r over 2 times dB dt. Okay, let's look at another example now of how we can use this equation. Okay, so in this example, we have a long solenoid. So it's a coil of wire like this, and it goes on some current flowing through that solenoid, and we're told that the current is given the equation I is equal to I max cos omega t. So this is a typical equation for an alternating current, and we're told that this solenoid has a radius capital R and it's got n turns per meter. Okay, and then in part A, we're asked to determine the magnitude of the induced electric field outside the solenoid at a distance little r is greater than bigger. So what we're going to do is take something like this with a radius r, and we need to calculate the electric field there. So let's draw a loop around like that, and we're just going to have a bit of a look end on, because that'll make it a bit easier to see exactly what's going on. So we've got a loop with a radius little r, and then inside we've got a solenoid here with a radius bigger. And in order to work out the electric field, we're going to use that the electric field dot ds is equal to minus d phi b dt. So from this you can see, well, we're going to need to work out what phi b is. Phi b is equal to the integral of b dot dA. Okay, so looking at this, we know that close to a solenoid, but outside it, we've got zero magnetic field. That's because if we draw a solenoid like this, then the magnetic field lines go around like this. And as long as our little r isn't massive, then we're in this region here with zero magnetic field. So if we coloured in that region here green, then in the green region there, we've got zero magnetic field. Okay, so if we want to work out the flux, then we've got flux through this middle area, but not through this green area because it's got zero magnetic field. So through the middle area, well, this is a solenoid, and Ampere's law told us that B is equal to mu naught Ni for a solenoid, and I is given by this expression here. So the flux is equal to mu naught N. Now I is equal to I max cos omega t, and the area that we're considering is this pi r squared. Okay, so now we've got our expression for phi b, we can go back over here. Now around this loop, it's reasonable to assume that the electric field is constant because it's completely symmetric, so it wouldn't make sense for E to be different have a different magnitude on the different sides of the loop. So we've got E times ds, and this is the integral around that loop. So it's just equal to the circumference of this circle here. So E times 2 pi little r is equal to minus d, and then this is phi b, which we've calculated here, mu naught n I max cos omega t pi r squared dt. Now we've got E times 2 pi little r, and now we need to differentiate this. Constants mu naught n I max times pi r squared, and then we've got d cos omega t dt, and so, well, and we've dropped our negative, and this is equal to minus mu naught n I max pi r squared, and then differentiating this, we'll end up with minus omega sine omega t, and that's equal to E times 2 pi r. We're trying to find E, the electric field strength, so these pi's cancel out, and we end up with E is equal to, well, the negatives cancel out, so we get positive mu naught n I max r squared omega sine omega t over 2r. And that's our expression for the induced electric field strength outside that solenoid. Now in part B, we're asked to calculate the induced electric field inside the solenoid at a radius r. So now little r again, but in this case we're considering this little blue circle here. So if we consider the magnetic flux through that little blue circle, well, the magnetic field strength is given by this expression again, B equals mu naught Ni. So mu naught N times I, which is I max cos omega t, but in this case we're only considering the area inside the blue circle, so that's pi r squared, little r squared in this case. So we can use this same reasoning exactly for this left hand side. So we've got the E dot ds is equal to 2 pi r e, and that's going to be equal to minus d dt of phi b, which is mu naught n I max cos omega t times pi r squared. And solving this, we have minus mu naught n I max pi r squared. And then we're going to differentiate this cos omega t. So we'll get minus omega sine omega t. And that's 2 pi r and e. And you can see one of these little r's will cancel out. In this case, the pi will cancel out. And we end up with e is equal to mu naught n I max little r omega sine omega t over 2. And so that's solved it for this second case. This tells us the electric field induced inside a solenoid. Okay, so this brings us to our last topic, which is self-induction and inductance. Okay, so if we imagine a component in a circuit which can act as which can get some inductance, so a little solenoid, say, then when we send a changing current through this solenoid, we're going to get a magnetic field induced. That magnetic field is going to oppose the change that induces it, and it's going to create an opposing current to resist the change. So we can say that the induced EMF is going to be proportional to how quickly that current is changing, because the current changing is what is inducing the EMF in the first place. So this L is actually our definition of what inductance is. And it's measured in units of the Henry, which is named after Joseph Henry, who actually discovered induction at around about the same time as Michael Faraday. Now, we've seen that the induced EMF is equal to minus n d phi b dt. So we can actually solve these two equations together to come up with a formula for inductance. So we've got minus L di is equal to minus n d phi b, and so you can see that Li is going to be equal to n phi b, which tells us that the inductance is equal to n phi b over I. Okay, now let's consider a circuit. So imagine that we've got some circuit here, input voltage. We can let it be AC so that we get a bit more induction, and we'll have a resistor here, and here's an inductor. So we represent inductors in circuits by little patterns like this so that it looks a little bit like a solenoid. So around this circuit, we've got the input voltage here. We lose a voltage equal to IR across this resistor here. And then across the inductor, we're going to lose L di dt. So we can write that the input voltage is equal to IR plus L di dt. Now let's consider the energy used by the circuit. The power, which is just voltage times time, is supplied by the power supply here, and it's used up by the resistor and the inductor. So just to get from this equation to the power equation, we can just multiply by I. So we've got that the power supplied by the power supply is equal to I squared R plus Li di dt. So this is the rate at which energy is stored inside the inductor. So we can write du dt. So yeah, this part is energy stored in inductor, and it's the rate. And so du dt is equal to Li di dt. So if we want to work out how much energy is stored there, we'll get rid of the dt's, and now we need to integrate, and we'll go from zero energy at zero current up to a total energy U at a current I. So we've got U is equal to, now integrating this with respect to I, we'll have L as a constant, and then we'll end up with a half I squared. So that tells us that the energy stored in the magnetic field inside the inductor is given by a half Li squared. Okay, so let's try a difficult problem now where we'll use this to calculate the inductance of something. Okay, so in this question, we're asked about a coaxial cable, and it consists of one wire here carrying a current I and with radius A, and it's surrounded by metal like this with radius B carrying a current I in the opposite direction. And we're asked to calculate the inductance of this system. And we know inductance is equal to N phi B over I. Okay, so for this case, we're going to consider a loop. We'll have length L because it asks us to consider a length little l. And we'll take our loop this way. So we have the current flowing down there and up this side. And we need to calculate N phi B I. N in this case, we've only got one thing, so it's just equal to phi B on I. So we need to work out, well, what's the magnetic flux through this area here. So when we were learning about Ampere's law, we showed that inside a wire of radius R carrying current I, we had a magnetic field strength equal to B is equal to mu naught I little r over r squared times 2 pi, where little r here is the distance inside the wire. So that would be at some radius here. And outside, we had B was equal to mu naught I over 2 pi r. Okay, so what we're going to need to do is work out the magnetic flux through this area here. So the center of the wire, that's r equals 0. We've got the radius A here on the edge of this wire and the radius B here on the edge of this wire. So to work out the flux, we're going to do the integral of B dot dA, and we'll sum up from r is equal to 0 to A, and then we sum up from A to B of B dot dA. These B's are different because they're in these different regimens here. And we know that dA is going to be equal to, this has length dr, so the dA is equal to L dr. Okay, so inside we've got the integral from 0 to A of mu naught I r over 2 pi. Now in this case the radius of the wire is A squared, and that's times L dr, plus we're going from A to B now. This is outside this wire, so we've got mu naught I L over 2 pi r dr. So integrating this, we'll have mu naught I L over 2 pi A squared, and then we're going to integrate r dr from 0 to A, plus mu naught I L over 2 pi times the integral of 1 on r dr, and that's from A to B. And this is equal to mu naught I L over 2 pi A squared, and this thing is r squared onto 0A, and this one here is mu naught I L on 2 pi, and when we integrate 1 on r, we get log of r AB, and so this is equal to mu naught I L over 2 pi A squared, and we've got A squared on 2, the 0 is 0, plus mu naught I L over 2 pi. Now this will be log B minus log A, so we can write that as log B on A. Okay, so now we've got phi B. L is just phi B divided by I. So these I's are going to cancel out, and we'll end up with our inductance is equal to mu naught L over 2 pi. Now this A squared will cancel that A squared, and we'll have another 2 down here. So rather than a 2 pi here, let's put this as 4 pi. plus mu naught, the I cancelled, and we have L over 2 pi log B on A. That gives us the inductance of this coaxial cable. And that's the end of this set of lectures.